About exponential growth versus linear growth. And sometimes when we look at growth, we have to try to figure out how is it actually growing? Is it growing linearly or is it growing exponentially? Okay, so some of the ways that we look at that. Now, if you think of an exponential graph, we're going to look at positive growth right now. The same thing applies. It's just the reverse of it when it's negative or decrease. But an exponential growth starts out slowly and then goes really fast up. A linear growth goes at a constant rate, like that. Okay, so what we're trying to figure out is what we're looking at going by a linear model or an exponential model. Depending which you choose, you get drastically different answers for the future. Okay, so that's something we look at. This is a constant multiplication. This is a constant multiplication. That's why it's called exponential. We're constantly multiplying the last answer by the same number. Okay? This is a constant addition. We're always taking the last answer and we're adding the same thing. So this is last number multiplied by the same factor. Okay, this constant is the last number, that's how it increases, plus the same number. Always adding the same number to get up there. So we have talked about this, that y is equal to abx. That's what gives us that constant multiplication. This is the number we're constantly multiplying by. So we are constantly multiplying by b in that case. Okay? In a linear equations, y equals mx plus b. M is what we are constantly adding to the last number. Okay? In this case, this is your starting number. In this case, this is your starting number. Okay, so they both include the same ideas, yes?
You gonna make sure a square root function?
No, we're not going to talk about that right now. Okay. There are other functions that we may model by. These are only two of the functions that we've been talking about. As you go farther in math, into advanced algebra, you will see other functions. Those other functions may represent your data even better. But we are just comparing today exponential versus linear. Okay, I do know, let me give a pure little thing for med. Was it meds?
I think it was math, wasn't it?
Was yours the one that kind of went up like this?
Yeah, it started to.
So meds growth went kind of like this. Okay, if you look at that, it really doesn't fit this. It really doesn't fit a straight line. Okay, this actually is a square root function. But you're not ready to learn about square root functions right now. So based on the shape, I can kind of tell you what kind of function it is, but that's what you learn as you go. Right now, we're just playing with the two, okay? So we're going to use now a problem that the people in Massachusetts did, their Department of Fisheries and Wildlife. So they were trying to decide if they wanted to allow hunting of the deer or not allow hunting of the deer. Okay, so what they went back to is years where they check to see if there was no hunting, how much did the deer population increase by? Okay, so what they figured out, these were figured out. So if hunting was allowed, okay, so hunting, this is when hunting's allowed. They found that every year 270 deer were added to the population. Okay, it was a constant rate of 270 deer increase. Okay, that's what they found from their research. Okay, now they found that if they did not allow hunting, it would grow exponentially by 15%. If they allowed or no hunting allowed, then, is that correct? Did I say that right? Yes, this makes sense. Then it grows by 15% each year. Okay. Which one?
So when hunting's allowed, is that 270 deer killed?
Per
or-
year. No. They increase the the
Okay.
population increases by 270 every year,
No matter what.
no matter what.
Okay.
270. If they don't allow hunting, then it grows exponentially because more babies have more babies, which have more babies. So you have an exponential growth. So the deer population will probably grow faster. What type of growth is the one where hunting's allowed?
Isn't that linear?
That's linear because we're adding 270 every year. Okay. What kind is the growth if no hunting is allowed?
It's exponential.
It's exponential. So they're saying that it will grow linearly if we allow hunting. That's what they found. They are saying if we don't allow that, it will grow exponentially. Okay, so they wanted to figure out something. They started with 85,000 deer. Okay, so their starting point, they started with 85,000 deer. Okay, so I want you to write the equation for this linear and write the equation for this one here. Put those on your paper. Okay,
For well, sorry.
both of these. So fill in the M and the B. Okay, for this, fill in the A and the B for this. You have all the information you need to do that right now.
So what's the question?
The question was to fill in and make the equations for both things. For hunting allowed and no hunting allowed. For you to think about so you can see how you're doing on thinking about this.
Yeah.
That number's not greater than 1. Number growth needs to be greater than 1, so we need to do that. Not quite that. It's a growth. You think it's going to decay? Right now you're decaying because that's less than 1.
What if I do that?
I don't know. What about?
You can show me.
Yeah, I can see.
There we go.
Yeah. Add that imaginary one. Might as well.
Add the imaginary one. I like you adding the imaginary one. Okay, so it looks like we're doing pretty good. So the constant increase here, what is the slope of this line?
278.
270. 270, because that's how much we're adding every year, okay? We started out with
85,000.
85,000. Because my beginning number goes here, I wrote that up there, beginning number here. How much we're increasing each year is here, okay? So what is this equation going to be? Max,
Y is equal to 85,000 times 1.15x
okay?
Mm.
So
to the power
is
of x.
why is it 1.15 and not just 0.15? Yes,
Because it would be decaying.
it'd be decaying, a decay. Remember, a growth. We know it's going to grow. A growing exponential, when it's growing, it's got to be larger than 1. So what you really have is your 100% that you had from the year before plus a 15% additional. Okay, so you have your 100% from the year before, plus you're adding 15%, that is 115% each year. So it's 1.15. That's why that comes in. Because these people are not dying. You don't get rid of the starting deer. You add just 15% more. Okay, so that's why you get that increase. Okay, so now let's predict. We've got A, B, we've got, okay. The number of, okay, we've done that. Okay, so the state allowed hunting. They decided to allow hunting. Okay, so which one are they going to use? Which one are we going to look at?
Linear.
The linear equation, because they allowed hunting. Okay, this started in 1998, so our beginning year was 1998. That's not good enough. They wanted to know in 2006 how many deer, or this is what they're estimating, how many deer they have left. So what would you put in as X? In my equation, what would I put in as X? Yes.
6, or not 6, 8.
Okay, 8, because 2006 minus 1998 equals 6. We know it's been 6 years. This is the formula we're using. So they're saying that, okay, we predict in 6 years to get this many. So tell me how much that is. Yes.
It's 8 years, not 6.
You're right, thank you. You said 6 to begin with, and that's where my brain went with. So thank you. Got my brain on a 6, and I didn't do it. Okay. Yes, it's 8. So somebody calculate that on their calculator. Yes.
87,160.
87,160. Okay, so if they didn't allow hunting, by the year 2006, they would have about 87,000 population of deer. Okay, let's say they didn't allow hunting. How many deer would they predict to have now? We're going to put this in as 8. So this is 2006 if they allowed hunting. If they didn't allow hunting, let's see how many deer we'd have now. Can somebody do that for me?
260016.
260,000.
17, because you're going to want to round up.
260,016.
Why was the deer missing an eye or something?
Yeah, he's
With the
missing
round
part of
the-
him, yeah. He's a three-legged deer,
Yeah.
yeah. Okay. Difference in growth, don't you think? That's only 8 years.
Not that much.
87,000 to 260,000, that's like 4 times the amount of deer?
Yeah, it's only 4 times.
Yeah, only 4 times, okay? Now, this is, but what if they had predicted hunting allowed and they came up with formulas, one was linear and one was exponential of the same thing? Would they be different answers? Do you see how different those are? 6 years, okay? They're quite different. Now, yes, growing by 15% is not the same as adding 270, but it's quite different, okay? People make mistakes. They try to say that stuff is growing exponentially when it may be growing linearly, okay? They can get a good program, okay? I will say the one area that they do this in, where they did this in, there's 2 areas that I think stand out the most. One is when you look at the actual temperature rise, we only actually measure from about 1870s up till now, so to 2025, okay? When you look at that temperature rise, both, so this is when they go out and measure and say this is the Earth's overall temperature, okay? When you look at that, the actual amount, which we'll talk about in a little bit later, but the actual amount is very, very small. It's between 0 to less than 0.2 degrees a year.
Is that Fahrenheit or Celsius?
That's Fahrenheit, okay? So from, this is 0.1, this is 0.2. We are growing. It has grown, okay, a little bit, but we are only going from 0.1 to 0.2. So they have tried to fit exponential models to this, and they have, so some does an exponential model and it fits. Another person does a linear model and it fits.
So it fits on both.
You can get both them to statistically be okay. That means that their numbers would be predictable in that little section of data we have. So by statistical significance, which is how well the model fits, within this model, both an exponential and a linear fitted well, okay? But if you go outside the model, guess what's going to happen? If it's exponential, it's going to go really fast. We are going to have melting caps, polar caps, okay? Because it's going to warm up tremendously in 50 years. But if we go linearly, which remember, both of these statistically fit the pattern very well. They make good predictions inside. But if I do the outside prediction, it's going to be way less than this exponential. So hence why you hear people saying we have to do something about global warming right now, because they're basing it on exponential growth.
We'll be dead by then. Who cares, really?
Well, not based on some of their models.
Oh yeah.
Okay,
We're
depending
like,
on how fast they're
2026 we'll
growing.
be dead.
Yeah. But also there's this fact, it could be linear. And that means maybe by 2020 or 2100, when we will be dead, 2100, well, some of you might still be alive in their 90s.
But the
Yeah.
rest of y'all will be dead.
Oh, brother.
I'll be 92.
Yeah.
I
So
might still be.
Imagine there's
you
a
actually died at
possibility.
92.
there's a possibility. Okay, so let's say
99.
2021. Okay. 2100, sorry. At 2100, this prediction is gonna be, it's awfully warm because it went up exponentially.
But then it's gonna cool down.
Well, we don't know, but I mean, that's the other thing, does it cool down?
It's almost
It
like it
does.
This
fluctuates.
prediction, we may be up to adding a half a degree or 1 degree by then. Because remember, this is between 0.1 degree and 0.2 degrees right now. That's all it is. We're not growing much. Okay?
Well, in the 1400s,
We couldn't measure temperature. We have no accurate measure of temperature in the 1400s.
well, we know from reports and letters that reason why the Commonwealth of Lithuania moved from up northern to down south is because
It got colder.
it got colder, and
Yeah.
then they moved back up because it got warmer.
Yeah, so I'm not gonna go back into but the recorded measurements, which even the recorded measurements are not accurate. Do you know why? They have to make alterations to the earlier measurements because they were done on different instrumentation, so they're making alterations to the data before they start using the data. If you go back and look at the true data, they had to make alterations to that data, so they manipulated that data based on the instrumentation that took those measurements. So we really don't know, we can't really compare apples to apples. It's kind of like Med when we were saying, you have to compare median to median.
Yeah.
You can't compare median to average. Those are two different answers, two different numbers, okay? So that's part of what you need to look at. So your assignment, there's two things, two parts to this assignment. I'm gonna keep recording this because I want you to. Your assignment now, which I am actually gonna have you use Desmos, and I'll go through that, to get your linear function, okay? So, you have right now in your project, at this point you should have an exponential equation that somewhat models, depending on, some people's will be better than others, somewhat models your data. From that, we can find predictions in the future, okay? So I want you to look at those, okay? So that's what we've done up to this point. We've done some modeling, okay? I had you do the modeling by hand. Now I'm gonna have you do the modeling by computer.
So you want us to
Okay.
see like in 200 years if ours is still right, kind of?
Kind of, that's what
Yeah.
we're
Just kind of see
predicting.
what it looks like,
Yeah,
if
yeah.
how accurate.
So now what you're gonna do is take your data, and what we're gonna do is find a linear equation that models it, okay? To do this, you go into Desmos. This you might want to write down. If we have computers, you can do this in class. I'm going to take you there right now, or take you through the process. So just go to desmos.com.
I do it on my phone.
May I do it on my phone?
Yes, I don't care. Okay. You want to open the graphing calculator when you go to desmos.com. So open graphing calculator. Okay. You're going to go up into the left-hand corner, and there's three lines. Left-hand corner, 1, 2, 3. Click on that. Okay? So when you click on that, it's going to give you a list of choices. You want to scroll down. So scroll down to statistics, linear regression.
You're so smart, Grayson. I remember this before.
He did this before. Okay, so once you scroll to that, so it's a ways down. They're not in alphabetical order. You just have to go down to it. Then you open the graph. It will say it has a graph, and you open the graph. On the left-hand side, you will see a table. The table already has numbers in it. You are going to put your numbers in there. Please put them as 0. So don't put in 1978. Put your first year as 0. Okay? Then if it's 5 years later, you can put 5 years as the next number, or just 2, and then it's 5-year periods. Okay, so depending on how you're doing that.
Don't you mean 1? Because it would go 0, then number 1.
Yeah, so 0, 1. If it's 5 years, you can do it per 5 years, just like your exponential is, then it's consistent. So put those numbers in, and after you put them in, it will draw a line for you on the graph, and you will see it will give you m equals, under the graph, it will give you m equals and b equals. Okay, so you can find your linear equation. Wait, shh. Okay, once you get your linear equation, because you've got m and b, then I want you to do the same predictions. Find the same years predictions. So I want you to be able to compare them. If you did this in 2050, then do a 2050 in this one. Okay? Put your x in, so you're comparing 50 years exponentially, 50 years linearly. What is your growth rate? What does it look like? So I want you to compare for all 3. Do for all 3. Okay. Then I want you to talk about which one does a better job predicting. And if you don't think either one does a very good job, then tell us that and say it probably is a different function. Okay, tell me that. Okay, questions on what you're to do on this assignment. Okay, so I will also put this in, but it's also being recorded right now. So if you need to know what to do, you can come back to the recording. It will tell you. Okay. And so that's in there. I will also put it in on your assignment. Okay. Then added to what you have, you're going to do 7.7, number 12. One of those, you have 7.5 and 7.6 to do. I will write those up here.
Oh,
So-
we have one question. From
7 is one question, because I'm really having you do this project. Okay, so I want you to spend time on that.
When's this due?
It is due, the project will be due next Tuesday. This number 12 will be Monday like normal. So these are due Monday, and the project will now be due next Tuesday, a week from today.
I don't know if that's.
What is today, the 18th, so that must be 3/25, March 25th, it will be due, okay? Okay, questions? Otherwise,
The years.
you get time to work on your project and your problems today.
Can we go down?
Go take a break now.
Can we go downstairs to get like food from?
You have to ask them.
What are you
You can't just steal